Welcome to lesson 9.06. We're going to continue here with volume. We're going to calculate the volume of solids formed by revolving a region around any horizontal or vertical axis using definite integration. Let's get started. All right, let's start off here with the problem. A solid is formed by revolving the region R, here it is, about the line x equals 4, which is this vertical line that runs right along the edge of the region. And we want to find the volume of the solid. So follow sort of the protocol and the intuition that we have used previously to find the volume for solids of revolution, and you'll be able to do just fine here. Take your time and be very careful. All right, now certainly you may be able to just see the cross sections right off the bat and be able to draw one on your own and go from there, but I'm going to continue, at least for the beginning, sketching the actual solid itself to get some intuition behind what's happening. So here I've drawn this over again, and remember, to sketch what this will look like, what I need to do is reflect my curve that forms my region about the line which I am rotating around or revolving my region around. And that will allow me to then draw circular cross sections. As you remember, what we're doing is we're taking each strip of this region and rotating it all the way around the axis. And so those are going to form those thin little cylinders. So here's my reflection, and now I'm simply going to draw the circular cross sections through my figure. Like so, and if I want, of course, I can sort of fill in the figure to make it look even more three-dimensional there. All right, so I have this sort of dome shape here, and now I can clearly visualize what each cross-section will look like. I can go ahead and sketch one singular cross-section and label appropriately. So here's my cross-section. Notice I've used a nice shape from the app, but you can just use an open circle and make sure you have the dimension here, which is the radius. And now I can really see my plan taking shape. If I can find the area for my cross-section, I know that the thickness of the cross-section is this thin strip along the y-axis, it's dy, and so I'm going to be summing up these infinitesimally small volumes of my cross-section through, as I cycle through the y values, going all the way up to the top of my solid here. So how do we compute the area of a circle? We need the radius. And therefore, our task is to determine how to compute this radius here. And to make this easier, simply look at our cross-section, and in the plainest language you can, tell yourself what are the components that go into determining this radius, and what do I have to do with those components to determine the radius. All right, once you see it, it will make a lot of sense. Notice that the radius is going to be built by taking the value 4 and subtracting whatever the x-coordinate of my curve is going to be. And you can see that very clearly if you look at the very bottom. Clearly, the radius here is 4 minus 0, the x-coordinate here. And as I move up, I'm going to notice that my radius will be getting smaller because the x-coordinate of my curve is getting bigger. And so therefore, at any point along my solid, the radius will be 4 minus the x-coordinate of my curve. Now, that means I need to write an expression for the x-coordinate of my curve. I currently have an equation that gives me the y value of my curve, but I want the x-coordinate. So I'm going to need to solve for x in my, using my equation here, and then write the radius. I've done that here, and the x-coordinate of my curve can be given by the equation x equals 4, whatever the y-coordinate is, squared over 9. Therefore, my radius is simply going to be 4 minus this x-coordinate, or 4 minus 4y squared over 9. And thus, I can write an equation for the area of my cross-section. Note it's going to be in terms of y. I'm going to be summing all of those volumes along the y-axis. And it's going to be pi r squared. So pi times our radius, which is 4 minus 4y squared over 9 quantity squared. Now I can simply incorporate the thickness of my cross-section dy and use a definite integral to calculate this volume. And I've written that here. Notice I'm simply applying our definition for volume, and then here I am simply inputting the function for the area of our circular cross-section. and I factored out a pi here. Now, notice at this point I can simply integrate using a calculator, but if you were stuck doing this without a calculator, how might you do that? Now, there's a couple options. You could go ahead and actually multiply 4 minus 4/9 y squared times itself and then integrate term by term. But multiplying this by itself won't be very fun. But you could make it a lot easier if you could factor out the 4/9. So I'm going to show you how you might do that, and you could apply this to a bunch of different situations. So let's take a look. I'm going to pull this out here and we'll look at it. Alright, so I'm going to pull out a 4/9 from both these terms. So what I will have left is I have 4/9 times, okay, so what's going on in here? Well, 4/9 times what will give me 4? It's going to be 9 minus y squared. Okay, so take a look at that for a second. Notice that if I were to multiply this 4/9 in, I'd end up with 4 minus 4/9 y squared. Now, since I have something times something else, and they're being squared, I can square each term separately. So I can square 4/9 and I can square 9 minus y squared. Well, 4/9 squared is 16 over 81. And then over here I have 9 minus y squared squared. Well, I can multiply 9 minus y squared by itself, and that won't be so challenging. And I can factor out the 16 over 81. So I can rewrite my integral as follows, where you'll notice I've factored out this 16 over 81, and then I have actually taken 9 minus y squared and squared it to get 81 minus 18y squared plus y to the 4th. Then I can find the antiderivative, evaluate at 3 and 0. Notice the antiderivative is going to have a y in each term, so when I evaluate at 0, it'll be 0, which will make my life a little easier, and that will allow me to compute the volume. And after doing so, as I've done here, I'm going to end up with 128/5 pi units cubed, and that ends up approximating to, let's see, about 80 units cubed. All right, before we move on, I want us to note what made this problem challenging and how we dealt with it. This problem had an axis of revolution that wasn't the y-axis or the x-axis, as we have seen previously. And so that makes defining the dimension of our cross-section that we need in order to compute the area a little more challenging. But as long as we take it slow and we follow the way that we did it here, you should be fine. So let me go over that once more. We knew we needed an expression for the radius of our cross-sections. And in order to come up with it, we just asked ourselves this simple question: what components go into computing this radius? Those components are simple. It's the line x equals 4 and the curve 3 over 2 square root of x. More specifically, it's the distance between those two curves horizontally, or the distance between the x-coordinates of this line and the x-coordinates of our green curve. The x-coordinate of this line is always 4, and we can write an expression to give us the x-coordinate of our green curve, which we did over here. Once I have those, I can combine them appropriately. Since this line here always has the bigger x-coordinate, it will be 4 minus the x-coordinate of our green curve, as we have written right there. That allows us to then write an equation for the area of each cross-section, and in turn will then allow us to compute the volume, as we did right here. Let's quickly add that to our notes and then try one more example before we move on to the homework. Alright, so let's add this last piece here to our notes on volume. When we are dealing with a solid of revolution, the axis of a revolution can either be a vertical line or a horizontal line. A vertical line like the y-axis, the line x equals 0, or it could be any vertical line, x equals anything. Horizontal line like the x-axis, y equals 0, or any horizontal line, y equals anything. Regardless, here are the steps to success. Take time to clearly state how your dimension or dimensions of your cross-section are calculated. Ask yourself, what components will create that dimension? Just like we did in the previous problem, we asked ourselves, what components go into determining the radius? And once I've stated that, I want to write an expression that represents your statement. So my statement was, it was the x-coordinate of the line x equals 4 minus the x-coordinate of the green curve, and then I wrote an expression that actually stated that mathematically. Those are going to be the keys to success. Now, overall, it is important to notice something important about volume. Whether we're dealing with a volume where we're given a base, a type of cross-section, and the orientation of the cross-section, or whether we're revolving some area around a vertical or horizontal line, the key is finding the cross-section and finding a formula for the area of the cross-section. It's also really important to know which variable we're going to be integrating with respect to. Are we going to be going along the x-axis or the y-axis? And hopefully what you've seen by now is that there is a pretty clear distinction. I'm either going to have cross-sections that are perpendicular to the x-axis or cross-sections that are perpendicular to the y-axis. If the cross-sections are perpendicular to the x-axis, then we're going to integrate with respect to, that's what WRT means, with respect to x. In other words, we're going to be adding those cross-sections as we travel along the x-axis horizontally. If we are looking at cross-sections that are perpendicular to the y-axis, then we're going to integrate with respect to y. In other words, we're going to be adding those volumes as we travel vertically. And so we'll calculate our volume by integrating with respect to y. Remember, we're looking at what are those infinitesimally small thicknesses for our cross-sections. Will it be dx or dy? All right, now we've learned everything we need to learn about calculating volume. Let's go ahead and practice a little bit more with one more example. All right, let's try this problem here. What I want you to do is go ahead and write it down, come up with a plan of attack first, then press play. We'll talk about a plan of attack. Make sure that you're solid on what you're going to do, and then you can do it and then check your work. All right, obviously first I'm going to need to sketch these curves so I can figure out my region. I'm also going to want to sketch the axis of revolution, y equals 1. If I want to, I can actually sketch out what this solid will look like, but we don't have to. What's key is that we actually are able to sketch the cross-section for the solid and then find the dimensions of the solid in order to write an equation for the area of the solid. And then I'm going to integrate using my definition for volume to find the volume of that solid. Okay, give this a try on your own and we'll take a look at the solution together. Okay, so here is the sketch of that region. They intersect, the two curves intersect at this point, and this region is going to be revolved around the line y equals 1, and I've actually drawn that revolution here. You'll notice, of course, there's a bunch of space between the region and the line, and so that's going to create this hollow interior. So in between these green cross-sections is hollow, and then in between the green cross-sections and the red cross-sections is actual solid. All right, and so looking at my my picture that I've drawn here, I can actually see what the cross-sections are going to look like. It's going to be this these cylindrical pieces where I'm taking each strip and I'm making a cylinder, but there's going to be a hollow on the inside. And so I can go ahead and just draw one of those right here so that I can then pinpoint the dimensions I'll need and find the area. All right, so here is that cross-section. Notice it's a washer-shaped cross-section, so the area that we seek is the area between the red circle and the green circle that we have here. And if we want that area, we need the area for each circle and therefore the radius of each circle. All right, let's start off with the radius for the red circle. Notice that this radius that I'm outlining here is going to be calculated by finding the vertical distance between the line y equals 1 and the curve y equals x squared. And since we're looking at a vertical distance, that is the difference in the y-coordinates. And if you recall from when we started with area, we can find the vertical distance between two curves by taking the one with the greater y value minus the one with the smaller y value. So the y value of this curve is 1, obviously, y equals 1, and the y value for my curve, the red curve here, is x squared. So the radius, capital R, will be calculated by doing 1 minus x squared. Lowercase r is pretty much the exact same reasoning. It's going to be the vertical distance between the curve y equals 1 and my green curve here, y equals sine of x. So that's going to be the difference between the y coordinates, so it'll be 1 minus sine of x. All right, at this point, I am ready now to write a function for the area of my washer. It's going to be in terms of x, and remember, it's going to be the area of the red circle minus the area of the green circle, and the area of the circle is pi r squared. So I'll have pi times 1 minus x squared squared minus pi times 1 minus sine of x squared. And I'm going to go ahead and factor out a pi since there's a pi in each expression. So there that is. You can see here clearly if I factored the pi back in, I would have the area of the red circle minus the area of the green circle. And now when I combine the area with the thickness of each cross-section, which is simply dx here, I will be able to find the volume, infinitesimally small volume of each cross-section, and using the definite integral, I can sum all of those up. And notice here I'm going to be summing along my x-axis, and I'm going to go from 0 to the point where they intersect, or 0.876. So my volume will be calculated as follows. Notice, of course, that I am simply applying my definition for volume, and here I am then inputting the formula I found for the area of our washer-shaped cross-sections. I've factored out a pi, and no need to do this by hand. We'll simply use the calculator and compute the volume to be 0.573 units cubed. All right, at this point, go ahead and move on to homework 9.06.